Hello, in the last video I tried to give you some intuition about time complexity, and I also wanted to introduce the classification of time complexity for which I didn't have enough time. So in this video I'll give you a brief introduction to the classification of complexity classes. So complexity classes classification. So you know when you have a good algorithm. Good algorithm basically means it has low complexities, right? Low time complexity, low space complexity. That means it occupies less space and lower and other and less dependencies on other factors, like uh, uh, do some specific architecture, right? That particular algorithm works only on this particular architecture because of some instruction sets. So a good algorithm is one that has less complexity and less dependencies. So yeah, this is something, and let's get back to the classification. And if I have some straight line representing the complexity of some class of algorithms, uh, I could divide it into four known classification parts. The first could be P, or from here, the easiest one that you don't require very much thinking or very fast, and like one. Here, these algorithms are P, or polynomial type algorithms of it. Their complexity is polynomial type, right? The most we mostly come across polynomial type algorithms. Uh, you know, line drawing algorithms. We have a lot of polynomial type algorithms like Belfort. Uh, so we have dealt. Any computer programmer has dealt a lot with polynomial type algorithms. Then we have the NP. This is very interesting. This is again polynomial type algorithms, but when processed by a non-deterministic machine. Uh, we don't really have non-deterministic machines. This is just a theoretical magical model, and I'll just get back to it. Then we have a bigger complexity, that's exponential complexity. Exponential complexity would basically mean brute force, right? Brute forces are generally part of exponential complexity. So yes, exp. And then I have R, all the decidable problems, all the problems to which I can arrive at a solution in finite time, no matter how long it is, right? Like maybe in 100 years, given that it's correct. And the rest above, till here I have my R thing, and here I have the undecidable problems to which I have no solution for. Or I wouldn't arrive at a solution in finite time. That means never, right? So I'll never arrive at a solution. So it's just a way of saying I'll never arrive at a solution. So problems of this class can have a solution, right? Arriving at a solution in finite time means you will never arrive at a solution. That means you don't have a solution. Yeah, so it's very interesting here that if we generally think there are a lot of problems in R basically means even some stupid person who wouldn't try brute force would think his problem to be, or his algorithm would be, in R. And brute force, systematic brute force, not just brute force, systematic brute force would be next. I mean, there would be no repetition, so that'd be next. Brute force, the way how I relate it is, when I played games like Halo, they were brutes, right? Brutes basically were monsters that seemed very, very stupid. They would just randomly shoot everywhere. But let's consider a smart brute. Okay, he'll only shoot in a direction once, and obviously there is some possibility that he will surely shoot you, given that you're standing at a distance. The farther you stand, the the less probable will be for him to shoot you. So that's like the way the complexity increases. So my smart brute is going to shoot in a direction only once, right? So that's going to be brute force. That's because in the worst case scenario, his last bullet, the last slot would be the place where you're standing, and in the best case scenario, he'll just shoot you directly. So that's brute force x. That'll be an exponential time. The string input could be related to the distance to which the distance at which I'm standing from the brute. The algorithms in R are like, they are more like brute forces, but they are not very systematic. The brute is, shooting randomly, just randomly, and hoping to hit me, and that's not a very good algorithm. Obviously, P are basically the algorithms that we know that actually solve a problem. A good solution, or most standardized algorithms are in P. And then we have NP, non-deterministic polynomial type complexity. This, NP could be related to, the mathematical type, right? Because you have a non-deterministic machine that, as long as there's a path to an accept state, or to a halting state, or to some state to which the machine stops, it arrives at an output, correct output, it'll find that path, right? No matter how many different sort of paths it could have, it would still arrive at this final accepting state. And it won't try all these paths. It's not like that brute who'll try or who'll repeat. It's this special kind of brute who'll just guess, okay, I'm gonna hit this spot, and it'll be right. And it'll just guess, a very, very, very lucky brute. He'll just guess, keep on shooting, and maybe mirrors here, and it'll hit you, right? So this is non-deterministic brute, or non-deterministic computer. So yeah, this is a very, very lucky brute, and I hope you never face one in it's a video game. So something like this is obviously not very realistic. You cannot be very, very lucky unless there's a parameter like the brute can see you, it judges some way, but it cannot be very standardized, or if it can be, it's still a mystery. That's why so basically it's guessing and arrive at a solution, and you'll basically verify the solution, right? So you don't exactly solve it, you guess, and you know that it's correct, so you verify the solution, right? So it's pretty nice that, okay, the brute keeps on shooting, he arrives at you luckily, and every time he'll shoot in the right direction so that he's led to you. And what the task of the computer would be is to verify that this is correct. So it'll basically implement the rules of physics, and that has to be in polynomial time. So people also state NP complexity as you don't really solve the problem, you have to be able to verify the solution, or verify whatever the thing is, the physics here, in polynomial time. So this is a very interesting case. And then we arrive at this P versus NP problem, which is also the $1 million problem. And this is basically nothing but you could either say P is not NP and P is NP. So in either way, you have to provide a solution satisfying either of this equation, and if that's correct, you get $1 million, and of course fame and a lot of things. And what basically this asks is, for every problem to which I can devise a solution in polynomial time, let's take this. Like P equals to NP would be, for every problem to which I can arrive at a solution so that the complexity is in polynomial time, can I also verify that in polynomial time? So if you can do, then it's P equals to NP. If I cannot do, then P will not be NP, and I have to provide a proof for that, and that's the big puzzle here. So yes, a very interesting problem. A lot of guys keep trying every year, and there's hope for solving it. Although another fun fact would be, most problems are after this part. Most problems are after R, or more complex than R. That means most problems are not solved, and that can actually be proved mathematically, and it's actually pretty simple. If you take and standard algorithm and you know how the way it's implemented, you can easily prove that most problems are not solvable by a simple state theory and having some knowledge about how to implement with algorithms, or just how to write a program and how to compile one, right? So that's it.